Okay, so this panel is panel 2. It's called Technology Innovations for a Sustainable Future. I added that last bit on just now, but I think it's appropriate. Professor Yang was supposed to moderate this panel. He emailed me last night and said he has the flu and can barely talk. So I've decided that I would moderate it. My name is Shapiro. I am the president of the Clean Green IGERT program. We're the ones that put this workshop together. So let me go through the speakers that we have for us. The format will again be 15 minutes per speaker and then roughly a half-hour discussion and then followed by lunch. We're going to start out with Dr. Linda Sapochak. Did I say that almost right? Okay, sorry. And she is from National Science Foundation, the Division of Materials Research. She has a really broad portfolio of research that she's funding, but I think she's going to talk about more in general or ask questions from us or start a discussion on what are the challenges in research and education for moving towards this future that we're looking at. As we heard yesterday from Professor Sachs, if we ascribe to that rather stark future that he described, we have to basically electrify the entire economy and make all the energy production completely carbon neutral, which is very ambitious. I'm sure there's a whole lot of economic development that will go into that, which is great, I guess, right? But how is that going to happen? So it's going to come from long-term investments by the government. So that's why we've asked Dr. Sapochak to come. And then next we have Russ Jones, who is a UCLA alum from material science, and he has a long history working with Boeing, and specifically recently he's now working for Spectrolab, and Spectrolab manufactures, I believe, the highest efficiency photovoltaics in the world. They're not cheap, but they are the best, and they're sorry. Cheap under concentration. There's the key, right? So they've been traditionally used for space applications, for satellites and Mars rovers and the like. And the question is, how do we leverage these really, really great photovoltaics for terrestrial applications? And not only that, how are they going to push the efficiency up even more? What's their game plan? That's what I'm interested in. I don't know if he can reveal all their secrets, but hopefully he'll give us some nuggets. And after that, I'm really excited. We have Professor Lynden Archer, who is the director of the Chemical and Biomolecular Engineering School at Cornell. And he's a specialist in hybrid organic, inorganic materials. So that interface between organics and inorganics. And it's a really hot topic right now because inorganic materials tend to be high quality but more expensive, and organic materials tend to be extremely cheap and easy to process, but not as efficient. So there's some synergy there that we can leverage, and specifically for energy storage. And then our final speaker will be Professor Liao, who's from UCLA, from the Chemical Engineering Department, and he is in his research group specializes in the production of biofuels directly from electricity, as opposed to sunlight, for instance, where you need these giant ponds of algae to make biobutanol or biofuels under the normal paradigm. And there's just all sorts of problems with that. How do you keep the algae alive? Is there too much light? Is there too little light? So the idea that you could make biofuels directly from electricity is huge, and they just published a Nature, it was Science, I read it in Science, Science article on this, which is fantastic. So the question then is it possible to, for instance, in 20 years when there's gigawatts of solar generating capacity, maybe electricity will be free during the day? I mean, if there's that much solar, electricity may just cost pennies during the daytime when it's bright out. Can we use that electricity then to make those biofuels to run our economy or store it in batteries? Is that a viable direction to go? That's kind of what I'm interested in hearing about. But anyway, so with that set up, I would like to start with Dr. Sapochak, and yeah, take it away.
So first of all, I'd like to thank Josh and Diana and the students from the IGERT program for inviting me today. I'm very excited to, this is energy and sustainability has been something that I've been working on since I started at NSF in 2008. And I think it's extremely important. And so I'd like to give you a general perspective, not just from NSF, but from government, because I have worked with Department of Energy and the Air Force talking about energy-related issues. So this gives you a little bit of an idea of what I want you to take away from my presentation. When I saw the flyer for the workshop, I was trying to figure out what should I talk about, what should I focus on. I can't just talk about NSF and all the great research that we fund. So one of the questions that we ask on the flyer is where the low-hanging fruit is with respect to energy technologies and innovation. Where should we be, placing our funding? Where should you be looking for opportunities to reach the goals that we'd like to make with respect to clean energy implementation? So I'll talk a little bit about that. Secondly, this idea about system-level thinking, it has been come up a lot in the last panel, and I think you'll hear it. You heard it from our last speaker yesterday from Columbia. You need to really be thinking about a lot of other things than science and engineering when we try to address these problems. So system-level thinking is key. And finally, I leave you at the end of my talk, just because something's clean doesn't mean it's sustainable. And that relates back to system-level thinking. So I want you to think about these three things as I go through my presentation. Okay. So here I show three documents. One is the Department of Energy quadrennial technology review document that was just published in September 2011. The Energy Horizons Science and Technology document that was just published by the Air Force, I think in January 2012. And then, of course, the National Science Foundation Strategic Plan. And I have to say I was lucky enough to be involved in and it's kind of funny in the DOE document and the Air Force document, but not necessarily in the NSF one. So they put that together at the higher level. But I'd like to read a quote from the DOE one. There is a tension between supporting work that industry doesn't, which biases the department's portfolio toward the long term, and the urgency of the nation's energy challenges. The appropriate balance requires the department to focus on accelerating innovation relevant to today's energy technologies, since such evolutionary advances are more likely to have near to midterm impact on the nation's challenges. So this document actually is really relevant to what we're talking about with respect to low-hanging fruit. It actually outlines where the nation needs to go and what technologies where they're at, where they need to go, and what new research that needs to be done in order for us to reach President Obama's goal of 80% of the nation's electricity from clean energy by 2035. I'm not going to talk about energy horizons. Of course, everything that the Air Force or the Department of Defense does affects our energy economy. Airplanes and fueling and our defense is really energy intensive. So they have a plan not only for funding research in areas such as storage, transmission, and their needs, but it's directly linked to the DOE quadrennial report. And as you'll see in both documents, they talk about partnerships between the agencies in order for us as a government to have an energy plan. So I have to beg to differ from our speaker yesterday. The government does have an energy plan, but it's not necessarily related to the issues of climate change as much as I think a lot of people would like it to be, and there's political reasons for that. So what about NSF? NSF, our mission isn't energy, but we certainly fund a lot of energy-related research. So I take one quote from our document. Our investments underpin long-term solutions to societal challenges. And of course, this includes economic development, climate change, energy, and cybersecurity. And what we do is we're looking at near-term actions to expand our partnerships and collaborations so that we can help these other agencies with their missions. So our investments in energy are related to making sure that we partner with these other agencies. So one example of that is the Sunshot program by Department of Energy. NSF actually partnered with DOE EERE to fund and to evaluate the proposals for the approaching $1 per watt PV. So we have been, in fact, been actively involved with the other agencies to reach some of these goals. Okay, another document talking about low-hanging fruit, giving you some insight into some areas that the government agencies believe are areas of research that could make an impact now, is in nanotechnology. So if you do a search for NNI Signature Initiative on nanotechnology, there's one related to solar energy collection and conversion. And this is an interagency collaboration and document that identifies, thank you, areas of emphasis that Department of Energy, NSF, NIST, NASA, and the Department of Defense think are important, and that they think nanotechnology will play a real role. Now, I'm not going to give, I could spend a whole talk just talking about details about this, but the three thrust areas are photovoltaic solar electricity, solar thermal energy generation and conversion, and solar to fuel conversions for nanotechnology. And going from thrust 1 to thrust 3, thrust 1 is more near term, and going down the line toward thrust 3 is longer term. So I encourage you to look at that document. There's a lot more details on the web with respect to what areas of research that they think that nanotechnology in these particular general topic areas can advance. Okay, so sort of information for you about low-hanging fruit, because I don't really know the answer, and I don't think any of us do. That's why we do these studies. Okay, so let me go into some. I mean, I'm from NSF, but we certainly, as I said, work closely with DOE, and it helps me to figure out when I get energy-related proposals what's important. This is there's a table in the DOE quadrennial report that lists a number of the clean electricity technologies and talks about materiality, the market, and maturity of these technologies. So I was telling you, near-term, long-term, and short-term. And materiality basically means the technologies could have big impact if implemented, big impact on the national energy goals within the 2 decades. Market means that there's available market for it, and maturity means that commercialization is realizable within the next 10 years. So it's really nice. This document talks about all these technologies. So let's talk about one particular one, and I didn't pick this for any reason except for as an example, concentrated solar power. If you look at that, it could be a material, meaning that it's a large resource, but it's highly regional. So it means we're using solar thermal to use heat to generate electricity through production of steam. You need large land use. You need water use. There's already a market out there. There's several of these farms around. But one of the things that's needed as far as technology innovation is the thermal storage. In the United States, the way that the heat energy is stored is in molten salts. And interestingly enough, I found an article that appeared in Forbes magazine just earlier this month. A young man who just got his PhD recently in mechanical engineering, working for a materials company in Silicon Valley, really, really interested in renewables. And so he decided that the bottleneck from keeping CSP from being competitive with natural gas was the storage problem. And that's part of the problem. And so what he did was he proposed to Department of Energy some ideas about some new salt mixtures, and he did get a grant for $1.5 million. And he's been successful spinning off a company called Symix. This was funded by, as I say, from Department of Energy. Why do I bring this up? It's an example of someone thinking about the system and trying to come up with alternative solutions that may not be out of the box and really, really creative, but are needed at this time. So I asked the question with respect to this particular example, is CSP can be clean, obviously, because we're using thermal to heat the molten salt that can store the energy, and then that energy can be released to create steam so that we can turn turbines and so on. But is it necessarily sustainable? And if you look in the quadrennial report document, and there's still a problem with water use. And there was some talk about dry cooling, which is a technology but it actually reduces the efficiency of the process. The other problem is with CSP, if you go to dry cooling, you need these very large towers that aren't very pretty, and they take up a lot of space. So you have to worry about the human factor, although these are usually in desert areas. So as I was talking about from my first slide, it's not just about the technological innovation. You have to worry about the economics, the social acceptance, the land use, and all of these things. So although this technology is clean, I would argue it's not quite sustainable, and we still need to work on that. So let me give you another example, something that's funded by NSF. This is work that's been done at Caltech and is funded by a number of programs for different aspects of it, from engineering and from the Material Science and Engineering Center's program in DMR. This is Sosina Haley. She's been working on using solar thermal heating also, but rather than storing it and making electricity traditionally through steam formation and wind turbine, traditional types of electricity generation, she wants to use the solar thermal heating of her materials to then produce fuels. And in this particular case, she uses cerium oxide, and at very high temperatures that can be created by solar thermal heating, cerium oxide gives up oxygen, and so you have defects in the structure. And as you cool it down, those defects in the structure really want to fill back up again. And so if you run water or carbon dioxide through this cooled down cerium oxide that serves as a storage unit for heat, then you can produce fuels such as hydrogen and carbon monoxide that can then catalytically be converted to methane. Is this clean? Well, sort of. Is it sustainable? Yes, sort of. So there's still a lot of things that have to be thought out from this very more fundamental research project. But these are the types of things that NSF is funding and challenging the community to think about, not just improving the efficiencies of these technologies, but thinking about the implications. Okay, so let's talk about a different type of technology that everybody's probably more familiar with, solar photovoltaics. Okay, in solar photovoltaics, the materiality is a little bit longer term. We have a lot of fundamental, large investments in energy frontier research centers. NSF has many partnered with Department of Energy and engineering research centers in the solar area. Currently, actually, within the last 3 years, the costs of solar have decreased by about 75%. But there's still significant technological headroom. So I just came back from the Materials Research Society meeting where we held a workshop called Facets of Sustainability. And we had a panel similar like this, and one was on energy. And Dave Ginley gave a presentation from NREL, and he showed the most recent chart for best research cell efficiencies for solar. It's much more complicated than when I was a graduate student. We have a lot more technologies to look at. But the question becomes, we've increased the efficiency by a number of technological innovations, and we actually, but the question becomes, what about elemental availability and scarcity, or the scalability of these things? What are the unintended consequences, as discussed by our speakers in the last panel, about scaling this technology up? And I asked Dave Ginley that question on the panel, and he talked a little bit more in detail about the emerging technologies, organic photovoltaics, the quantum dot photovoltaics, the sort of long-term stuff where using organic materials. Well, you know, those organic materials come from petroleum resources. So you're going back to talking and asking the questions about scalability, elemental availability, but you have to think about all aspects of the problem. And so I want to challenge you. I read a recent book called Abundance, and I thought this was really great. And actually, there's a TED Talk on the web by Peter Diamandis. He's the chairman of and CEO of X Prize Foundation. And it's a very fascinating talk. And basically, the book is The Future is Better Than You Think. And so I challenge you to read this. And what I took out of it, a quote, scarcity is contextual, okay? Something is scarce because we define what the parameters are around the availability of something. So technology is a resource liberating force. So I challenge you as scientists and engineers as you go forward and you are informed by the economic barriers and social barriers and environmental barriers, that technology is a resource liberating force. You can figure out a way to get around these things. And so I'm going to end with 3 slides. NSF is very interested, although we don't have a mission to fund energy-related research, we do, but we do have a mission to educate and to go into new directions. And so we have a large effort in promoting sustainability and promoting interdisciplinary research in these areas. So everything that I showed to you today related to energy was affected by society, economy, and environmental factors. And so sustainability is something that you really have to think about from a systems point of view. And with that, NSF is uniquely positioned to support this type of research as we are with this IGERT, which I'm very thrilled that I think that it's a wonderful opportunity for all of you young people to get together and think about all of these issues and try to figure out how your perspective affects other people's research. And all of these directorates and offices are involved in a program called Science, Engineering, and Education for Sustainability. And there'll be a number of opportunities in this area now and over the next few years. And right now, we're evaluating proposals directly related to what we're talking about. Sustainable energy pathways was the solicitation. It's basically identifying a technological problem and bringing in researchers from the other disciplines such as economics, social sciences, and environment in order to not only address the technological path, but the barriers along the way. And with that, I'd like to thank you. And if you're interested in these types of activities, you can visit the NSF.gov/C's website as we develop more opportunities for funding. Thank you.
Thank you.